Assalamualaikum dan salam sejahtera. Kita mulakan kuliah kita pada pagi ini. So from previous lecture, I already introduced you how to calculate the flow rate for piston pump. So the equation is Q is equal to A times L times N over 60, which is the A is the cross-sectional area and L is the stroke length and the speed. N is a speed rotation in minutes, means in RPM. That's why we need to divide by 60. And this is for single acting. But if you have double acting reciprocating pumps, you need to time with 2 because the volume of water that transfer from piston to the delivery pipe is twice for acting. For double acting reciprocating pump. So this is the slip of pump. So we could calculate by the idea of flow rate for theoretical minus with flow rate for actual and divide by the flow rate for theoretical. And we multiply with 100%, so we get the percentage of the slip of pump. So this is actually to represent how good your seal between your piston and your bore. And now I would like to continue these ideas by introducing you the displacement of piston. So the displacement of piston is very important because it shows the stroke of the piston. It shows us how about the volume that can be created by that piston. So this is the connection between the piston and also with the crank arm here. So, and then you could imagine that if this hinge is located at this point, so mean the piston will be here at the beginning of the suction. So, and then if this arm is rotated and reach at this point, so mean the piston is now actually at the back here. Mean at the end of the suction. So this is actually the volume that can be created for this piston pump. So and then if we see the distance created by this piston, we could say that the distance of x here, the horizontal distance x here is actually equal to the value of x here, which is we could write a mathematical equation for this x is equal to r cos theta, and the value of r is actually the radius of this crank of this rotational device. So and then why we need to determine the displacement. Another reason is because we want to calculate the velocity and also the acceleration. So why it is totally different with the centrifugal pump. In centrifugal pump, I think you already know how to draw a centrifugal pump. So we have a blade here. So let's say we have blade here. So and then this blade will rotate at constant velocity. So you know that the rotational speed for a centrifugal pump is constant. So mean if it is constant, so there are no acceleration. But for piston pump, you could imagine that piston will stop at this point and also at this point before it change the direction of motion. So means that from the you could imagine that the velocity actually start from 0 and then the velocity will increase at certain level and then it will slow down and stop. And then the velocity will again in reverse direction will go to the maximum one and then it will stop. So it occur again and again. So and I think you already know that velocity is a vector. So means if you draw a graph, so it will have the positive and the negative side. So that's the first thing. And the second one is because you have a difference in velocity. So as you know that we have V2 minus V1 over T, and then we could get this as an acceleration. So means that because we have change of velocity in this motion, so mean we could calculate the acceleration. So and then for this diagram, we could assume that the omega here is equal to 2 pi n over 60, which is the n here is RPM, rotation per minute. So this is actually the equation to convert the linear velocity to the rotational speed. I think you already know from the previous class. So the common relation is U is equal to R omega is equal to pi dn over 60. So which is the U here is actually the linear velocity. The unit is meter per second. And the R is the radius is in meter. And omega here is actually in radian per second. So radian is dimensionless. So the unit is still meter per second. So that's another thing I already said previously. So the N here is RPM. So means that if you have rotational per second, so you could use this equation without dividing into 60. So please be careful when you use this one. Please make sure that you are using the right terms with the right units. So then to calculate the velocity, so you know that we have the distance here, the x here. So to get the velocity here, UP mean the velocity for the piston. So we could differentiate this term, and you have dx dt, and you differentiate the r cos theta, and finally you will get r omega sine theta. So here, if you look back to your mathematics notes, might be you could say that we must add a negative sign, but actually we are now trying to avoid the negative, because negative is actually to show the direction only. In this case, we just need to know the quantity of that speed. So we omit the value of negative. So I already discussed about that. So I hope about this, you could imagine that the distance when the point is here. So let's say it is at this condition. So when it's rotate at this point, so it move forward like this. So it start here, and then if this point is at the back, so it will create the piston will stay here 2 times from here. So means that this distance is actually the distance that will give us volume in our piston pump. So and then from this diagram, so the distance here is called as a stroke. So when we have a question, if the question give you stroke is equal to 300 millimeters, for example, so please imagine that the stroke is actually the distance that piston can move from the beginning to the end. And this distance is actually equal to the diameter of this rotational device. Okay, so and then means that if you want to get the radius here, okay, you may get if you divide the stroke value here with 2. So you could write R is actually stroke divided by 2. Okay, why? Because if you see in this equation, we have the value of R. So and then we could calculate the continuity equation by use a common equation, which is Q is equal to A times V. So we have piston, for example. So we have the cross-sectional piston times with the velocity of piston. And then for suction pipe, we have a cross-sectional area for suction pipe times with the velocity of suction pipes. And AD is cross-sectional for delivery pipe, and UD is the velocity of delivery pipe. So then, because we have different in velocity, we need to calculate the acceleration heat, because the acceleration heat here represent the energy required to accelerate the water column in suction or delivery pipe. So how to get the acceleration A here? So we are just using a common equation, which is du over dt, means we differentiate the value of velocity in terms of time again. So if we do this, we could get the equation for acceleration is r omega square cos omega r omega square cos omega t. So this is the equation for the acceleration here. So and then the acceleration head is in suction pipe. So we represent the acceleration head as HAS. So H is head, A is acceleration, and S is for suction by this equation. So we have the length of suction pipe divided by gravity, and then we have cross-sectional area for piston divided by the cross-sectional area for suction pipe, and then we multiple with r omega square cos omega t, which is the acceleration. And for delivery pipe here, so we have HAD. So we have LD, means the length of delivery pipe divided by gravity, and cross-sectional area for piston divided by the cross-sectional area for delivery pipe, and we multiply with the acceleration. So in these topics, we are not going to derive each equation. So I hope you could remember this equation. So and then I think in Fluid Mechanics 1 and Fluid Mechanics 2, you already learned the importance to know the frictional head, because to make sure that we could transfer water from one point to another point, we need to overcome a lot of energy. And one of them is actually we need to overcome the resistance inside those pipes. So the resistance means the friction of pipe. So reciprocating pump, for piston pump, we will have our own friction head in suction and the delivery, and it is not equal, means that you cannot use previous major loss or minor loss equation for piston pipe. In certain conditions, yes, you could use that, but in general, right now, please imagine that you need to remember a new equation to calculate the friction for suction and delivery pipe. So this is only for the piston pump network, piston pump condition. So the friction head for suction is FLS over DS 1 over 2G, and its acceleration head. So you could see this equation. So and then for the delivery pipe, you just use all the parameter for the delivery, which is the length of delivery pipe and the diameter for the delivery pipe. So please remember the friction head in suction and delivery pipe. So and then, if you see this equation, so when we start to use the acceleration head, the acceleration in our calculation, you will find that the value of acceleration is actually changed because we have the terms of sine omega t. So sine omega t means you need to find the value of sine at so many point at the beginning, at the middle, at the end, and the angle is quite, and it keep changing from 0 degree from 0 to pi over 2 to pi and so on and so forth. So it means that sine omega t will give you a fluctuation value. So this might be make our calculation a little bit difficult. Then, okay, so we assume that it is okay for us if the question is not asking at what location of your calculation. So mean it is not mentioned whether it is at the beginning or at the middle or at the end of the suction or at the delivery process. So it is okay for you to use the average friction. So the equation for the average friction is 2 over 3 friction head for suction, and also 2 over 3 frictional head for delivery. So it is okay for you to this one because this calculation is actually based on the maximum value of omega, which is occur at pi over 2. So because we have the sinusoidal graph, I think you already know about this curve. So this is the pi. So and then it is the sine curve. So you will have the maximum value at pi over 2 here. So and then because the maximum is occur at pi over 2, we substitute the value of sine pi over 2, so we get 1. So now the maximum, the average frictional head for piston pump at suction and delivery is showing by this equation. So you have 2 over 3F, L over D, 1 over 2G. So AP divided by A R omega square. So when you want to calculate the suction value, so you need use to all the suction parameters as well as the delivery parameters here if you want to calculate the friction, the maximum friction head for delivery. So I hope you could imagine, remember this equation. So and then this is the equation for the power because we, as you know, in centrifugal pump calculation previously, might be to get certain amount we using Bernoulli equation and we need to calculate the head of pump, and then we use that head of pump into the power equation to get the power of that pump, because power is actually the common parameter used by engineers to show how strong our pump or the capability of pump to transfer energy. So because if you keep talking about the head, it's actually in some situation people are not looking at the head, at the pump head alone. So because power is actually give you a few meanings, because power is actually, it could include the frictional and so on and so forth. So and then so for piston pump, please do not use Bernoulli equation because the flow is actually fluctuated. So I think in the first notes for centrifugal for piston pump, you know that the energy transferred in piston pump is in periodically. Okay, so means that the water is not always full inside a pipe, so the Bernoulli equation is cannot be used. Okay, so and then however the equation for the power is remain the same, which is power is P is equal to rho GQ H. So which is the rho is the density of the liquid. So in our syllabus we always use water. We'll always use water. So sometimes might be I give you oil and so on, but normally we will use water. So it is okay for you to take as 1000 kilogram per meter cube. So gravity, and then we have the Q here, the flow rate, and we have the H. So the H here is actually will represent the total capability of piston pump to transfer water. So normally, okay, might be you remember the graph that I showed you previously in terms of the capability of piston pump to transfer water until at very high head of pump, which is 100,000 plus, compared with the centrifugal, which can transfer water at around 6,000 head, 6,000 meter, but the flow rate is higher compared to the centrifugal pump. Okay, so means but normally in our application we will have inlet tank and the outlet tank. Okay, means that our pump should be suit or should be fit with our application. So mean we for sure before you install a pump, you need to know where is your input and where is your output. Okay, let's say we have an input tank here and output tank here. So to calculate the total power need to be supplied to a piston pump, first you need to overcome the suction head. So you know the suction head is here, the level between the inlet and the center point of your piston pump. And then you need to overcome the delivery head. Mean at least you need to make sure that your pump could transfer water to the outlet surface here. So and then because it has friction, so we learned in centrifugal pump in Bernoulli equation previously about major losses, minor losses, and so on. So we need to overcome the loss in suction here and also the loss at the delivery. So that's why if you see this equation, you will find that the total head here, H, is actually the sum of suction head, delivery head, and frictional for suction, and also the frictional for delivery. So now I think you could understand, okay, why we need to calculate the frictional, because we want to substitute in power equation so that we could calculate the minimum power required by our piston pump to make sure that water could be transferred from the inlet to the outlet tank. Okay, so this is about the air vessel. So the air vessel can be fitted for one or both sides of the pump. So that means at the suction and at the delivery side. But usually people will install air vessel at the delivery side. So so this is just an information for you. So if the volume of air vessel on the delivery side is about 6 to 9 times the volume of cylinder. And if you want to install it at the suction line, so it is okay for you just to use about 3 to 4 times of the cylinder volume. So the air vessel here has a few functions. So the most important one is actually showing here. So first, it reduces the fluctuation of discharge. So as you know, previously I showed you the graph of flow rate. So if it's single acting, so it starts with the vacuum and then it's transfer water and then start to vacuum and transfer water again. So means that water water can be transferred at certain point only, at certain time only. So to overcome this problem, so people will use double acting piston pump. So flow rate will occur all the time, but as you know, it has a different of velocity. Mean the piston move in certain different velocity. It create an acceleration in motion. So means that the flow rate is not steady. So it will flow like this actually. But because we supply it at a very fast rate, for example, in 20 RPM, 50 RPM, so maybe we could get graph something like this. So and then for in high speed, we could feel that the water is actually flow at a constant rate, but actually it is not at constant rate. So if you have air vessel, so the area here, the lack of volume here, is actually will be top up at with the air vessel. So that it is this is actually the idea of the air vessel. So mean it will make sure that the fluctuation of at the delivery pipe will be decreased. That's why people install a bigger tank, a bigger air vessel at delivery pipe. So and then the pump also can run at higher speed because it less danger of separation flow. So separation flow means the water start to detach from the pipe, and then it can create some kind of bubbles and so on and so forth. So that bubble is actually could create impingement on the surface of the pipe. So it can lead to a micro crack, and then for high RPM and with the vibration of pipe and so on and so forth, it could crack the pipe and so on. So we don't want that happen. So we put an air vessel. So another thing is the calculation of friction loss. So will become small. The value of friction is reduced. So we could see this in our tutorial later on. You could compare with pipes. If you calculate in piston pump equation, you will find that the friction is actually higher. If you compare with same length of pipe, so the friction for steady flow is actually lower. So why this? So how we could create a steady flow? So we install an air vessel. Okay. So this is the air chamber or the air vessel. So you could imagine that if you pump water like this, so the water will go through the delivery pipe, but sometimes the delivery pipe is quite smaller compared to the piston here. So an extra water will flow into this tank. So and then when the water flow quantity, the flow rate is reduced, so the water from the air chamber here will flow to the delivery pipes to make sure that flow at this delivery pipe is constant. Okay, that is the idea. So and then for that situation, we found that the flow is become steady. So we need to calculate our velocity beyond the air vessel by using the idea of steady flow, means the idea of continuity equation, which is Q is equal to AB. So and then V is equal Q divided by A. So that's why we have ALN over 60 divided by the cross-sectional area of the delivery pipe. So this is the idea actually. So and then the discharge, the beyond air vessel can be shown like this one. So this is the idea of what I'm saying just now. Okay. So and then this is another equation to calculate the discharge in air vessel itself, but in our syllabus, okay, we are not focusing on the flow rate inside the air vessel. It is we only focus about the flow rate in the delivery pipe only. So okay, so this is for the double acting. I think you could read this one. And then finally, this is the total work that we could calculate for single acting pump with a vessel. So previously I give you one equation to calculate a power that is on for piston pump, the reciprocating pump without any air vessel. So if you have air vessel, you need to calculate like this one. So so the difference is we need to calculate of the friction loss here by using the idea of flow in pipe that we learned in fluid 1 and fluid 2. So, but don't worry, you could make a revision about this topic because in our tutorial, I will show you how to calculate this one.